But what I'm going to do is race through some history, which Alan started, and try and take you right up to some thinking at the present time. We have a new center at the University of Washington called the Center for Dialysis Innovation. And we've come to appreciate there are profound problems with how we deal with 2 million people worldwide who are on kidney dialysis. And one of the major issues relates to blood compatibility. And you'll see how that was important early on and still to this day remains a very important theme. So I'm going to start it at 1858, and this man, Rudolf Chou, is sometimes called the father of pathology. And in his truly classic text on pathology, he didn't do this triangle. He alluded to it, certainly, in the text. But the triangle says what is important about blood. It's the blood itself, the blood chemistry, the flow regime, and the surface. And to this very day, this is quite accurate. So people have been thinking about this idea of how to create a blood-compatible surface for a long time. And here's some papers from the 40s up to early 50s. Again, people are thinking about how one might make a blood-compatible surface. My own personal history in this area started, I was a graduate student at Brooklyn Polytech in Brooklyn, in New York. And my professor, my thesis advisor, sent me down to Washington, D.C. to attend a meeting which generated this red book. The book is about the size of the biomaterials textbook, so you know this is a weighty tome. This book was almost completely about the subject of blood compatibility and had hundreds of ideas, most of which are still quite relevant today on blood compatibility. And you know, if we take it up to the present, I'm not going to read this list at all, but of course, so many of the devices we routinely use function because they attempt to have some level of blood compatibility. Well, in 1972, I got into this car, or Renault, and drove from Brooklyn to Seattle to join Alan Hoffman's group. The car only broke down twice crossing the United States, and got me here. And this is a bit of what our group looked like in the early 1970s. And it was a smaller group, and there's some actually very illustrious people there. A number of people went on to become department chairman and things like that, and we could see Alan in the center. So, in fact, it's quite interesting. This fellow here, he's second person over here, was our dishwasher in our lab and is now considered the world's expert on radiation oncology of prostate cancer, but he started as our dishwasher. So anyway, a neat group, and this is where we got launched. And this is another one of the diagrams that come from Alan Hoffman's work. And it was talking again about this idea of taking a film, grafting a hydrogel, for example, on it. And we were funded by the, what was called at the time the Atomic Energy Commission, which was trying to develop a plutonium-238 powered artificial heart, which in retrospect was not such a good idea. But back then, everybody was very excited about nuclear energy. And our role really was not to work with this nuclear power source, but work with the blood contacting surfaces of the artificial heart. If you were doing blood compatibility work in that era, there were two tests that we really had to satisfy. You can see the scale bar here. You have these vena cava rings, which of course implanted in the vena cava, and one looked for thrombus buildup in the ring. Or the renal embolus test, where these rings were placed in the renal artery, and one looked both for thrombus buildup or for downstream material coming off the ring, emboli, that might leave infarcts or damage points in the kidneys. So everybody in the field was doing these uniform tests. Well, we started with our radiation grafting, and we were working with Jim Whiffen, I think University of Wisconsin, if I remember correctly, an MD, who did these implants for us. And you notice these celastic rings completely occluded with thrombus, where many of our hydrogel treatments, even some out to 2 weeks, were looking pretty good. So we thought, well, looked like hydrogels grafted the surfaces were the way to go. But then we got a report back from Bert Cousireau in Vermont, Dr. Cousireau, who did this renal embolus test. And I include the original report because it's kind of neat. It's typed on this thing called a typewriter. I don't know if anybody's ever seen one of those before. But anyway, this is the original report that came in the mail from Dr. Cousireau. And you know, we have we looked at 3 different hydrogels here. I think it's HEMA, NVP, and acrylamide. They're grafted at the surfaces. And there's a ring code, and these are pretty low numbers. It means there wasn't much thrombus there. But if you look at kidney infarct damage, right kidney, numerous infarcts, left 10 or more infarcts, right total damage, left very suspicious. So we thought we'd solved blood compatibility with these grafted hydrogels, and then we get this report back that said we were destroying the animal's kidneys. That was pretty much a surprise. So we came to appreciate that most people in the field at the time were really, you took blood into a tube and you look at what's stuck. And we came to think more in terms of a mass balance. I think it's a good chemical engineering thinking about it. So we have some number of platelets going into the tube, some number coming out. What happens in going through the tube? Can platelets be consumed or adherent? This thinking would measure all different cases. And that led us to work with Lawrence Harker, MD hematologist, and our former PhD student, Steve Hansen, who did go on to become a chair of the bioengineering department at Oregon Health Science Center. And, Steve, during his PhD thesis, helped develop the shunt model, a femoral shunt model. We had a little segment here, and we, even an engineer could put 2 clamps on and insert a piece of test segment and examine the reaction of materials to blood. So this is kind of what it looked like. We used a baboon because baboons were hematologically similar to humans. Steve worked out a very elegant kinetic model that allowed us to get a rate constant of reaction of platelets with the surface. We called it platelet consumption, but it has all the same units as a first order rate constant of reaction. It allowed us to get some very nice quantitative data. And our first data set was quite surprising, almost shocking, because we made a series of grafts with different hydrogels grafted to tubing, and then looked at the platelet consumption. And exactly the opposite of our hypothesis, the higher the water content, the more damaging it was to platelets. We had hypothesized exactly the opposite. And by the way, on the other extreme, we had quite hydrophobic materials, celastic, that seemed to have almost no platelet consumption. We could ask, platelets are being consumed, where are they going? Well, embolization is most likely with its potential consequences. So we worked with another colleague in electrical engineering, Professor Larry Reynolds, and Larry set up this very early laser scattering system that allowed us to look at these emboli being produced. This device used 8-inch floppy disks that held 140K of information on each 8-inch floppy disk. So it was pretty surprising. Actually, it's 80,000 bytes on these disks. So kind of different from today. In any event, with this sort of data, we saw that the celastic had low emboli production, and the hydrogels had very high emboli production. So again, this was consistent with our data and said that the hydrogel hypothesis was really, would not hold water. So let's see, we went on to look at polyurethanes. The NIH was doing, very interested in using polyurethanes at that time for the artificial heart, and we were then embracing the surface analysis techniques like ESCA, and did an analysis of the spectra, the surface spectra of the polyurethanes where we could look at what we might call the hydrocarbon or nonpolar component and a hydrophilic or polar component of the materials. We get that number. And when we looked at the percent of surface carbon atoms forming hydrocarbon bonds, in other words, more hydrophobic going up versus platelet consumption, again, we got a very surprising result. The NIH had a big commitment to the Stanford Research Institute polyurethane. It turned out to be the most platelet consumptive. And the biomer was also a major player in there, and the biomer was terribly platelet consumptive, where some of these other polyurethanes were actually very low platelet consumption. And again, this was totally a surprise to us. We've gone on since then. I did mention that our hydrogels look very poor, but there was another class of hydrogels that did not exist when we did that work, and this is what Alan addressed very much in detail, non-fouling surfaces. And for example, we have some evidence these days that the sphitter ionic surfaces and even grafted PEG may actually look pretty good in contact with blood, but we're still working on that hypothesis. Let's see. Yeah. So we also went on to vascular prostheses, and we were using glow discharge plasma deposition to make fluorinated weaves and grafts of Dacron. Another one of our hypotheses, and we were working with Andy Garfinkel, who went on to become an MD ophthalmologic surgeon. This is the glow discharge reactor that allowed us to treat these grafts and to fluorinate them. And we can take ordinary Dacron. Here's ESCA spectrum, surface spectra. This is what Dacron looks like. If we fluorinate it, we get a completely different type of structure with many different fluorinated species in it. And when we looked at the ability of these vascular grafts to remain patent over periods of time, the yellow bars are our fluorinated treated material. And let's just, for the sake of focusing, look at the red bar, which is an argon treated control. And in fact, the center bar, the striped one, is a weave of the type used in humans in large diameter vascular prostheses. So by 1 week, 90% of the untreated weaves were clotted or closed, and basically 90% of the fluorinated ones were still functioning in 1 week. Quite a striking difference. We could look at Doppler ultrasound data and see that the untreated weaves, the flow rate dropped. Well, we had very little drop in flow rate and are fluorinated. We could look at them and see that the fluorinated treatment had much less blood elements on it than the untreated. But you might say, well, this is sort of a Teflon-like treatment. Maybe all the clots just wash downstream, our emboli hypothesis. So we used the laser scattering system again and found that the fluorinated Dacron actually had fewer emboli coming off than the untreated Dacron. And supported the fluorinated. So remember, in the water content data, the very hydrophobic silicone looked great. On these treated grafts, fluorinated looked good. And so we started thinking a lot about fluorinated material. And of course, Gore-Tex, for example, is very widely used in cardiovascular medicine. So we started working on what we call the floral passivation concept. And the work here goes, it really is based upon some work that was pioneered by our colleague Tom Horvath, who, again, Alan and I worked with Tom our whole career. And Tom showed that, looked at the ability of many proteins in blood to bond platelets or interact with platelets. And fibrinogen, of course, was very bad. And surprisingly, things like fibronectin and vitronectin, we thought these were strong cell adhesion. They really were not that bad. And then full-strength human plasma, which has a lot of fibrinogen in it, was very strongly interacting with blood. But serum albumin, bovine serum albumin, was very low in its interactions with blood platelets. And we could look at a series of, for example, polyurethanes and rank them based upon fibrinogen absorption. But a lot of the thinking, again, to pay homage to some of our pioneers, Don Lyman at the University of Utah, back in 1974, was already publishing on the idea that there might be an area of non-thrombogenicity where you had high albumin on a surface. And where you had high fibrinogen, you get further reaction. So we developed some hypotheses, or updated Don Lyman's 1974 hypothesis to talk about albumin-fibrinogen ratios, the ability of albumin not to be displaced by undesirable proteins. That goes to Leo Vroman, another great pioneer here, and sort of blaming the blood compatibility issue on the fibrinogen that adsorbed to the surface. And we took a series of fluorinated or different polymers and materials that were all widely used in cardiovascular stents, in endovascular stents. And to test this hypothesis, we went through a whole bunch of different tests. I don't have time to read the list. But one of the important things was to look at the strength the protein was bound to the surface. So we absorbed protein, eluted with SDS, and looked at how much was left. If it was strongly bound, the SDS couldn't elute the proteins. We also did, by this point, we had some pretty sophisticated surface analysis gear. We did quite thorough surface studies on all these polymers to ensure we knew what we were working with. And I have a series of slides here. I'm going to go through them very quickly. But basically, they show various aspects of, in this case, it's adsorbed over eluted albumin. And the very first column, I guess from your side, it's the leftmost column, will be the fluorinated polymer. It's a hexafluoropropylene copolymer here, vanillidine fluoride copolymer. And what I want you to is look at the adsorbed to eluted number compared to the other materials. So this is how much we could really wash off. And 3 versus 49, 23, 27, it was very striking how different that was from the other numbers. And here's another protein absorption, 2.3 versus 1945. Very, very different number. Here's another one of these 2 versus 18. Again, mostly much higher numbers on these other stent materials. Here's a different one, but the value is 4 versus 23, 30, 54, 95. In every case, the fluorinated one had very, very different numbers, 3 versus 60, 20, 35. Something unique was happening in the way it absorbed proteins. It retained albumin and it basically absorbed more albumin. We could just go on over and over again. In every case, we got this very unique behavior for this fluorinated polymer. So sort of to tie together what I call 45 years of my own blood compatibility research, and again, it all started in working with Professor Alan Hoffman. I'd just like to conclude that Rudolf Virchow was actually right on. His ideas from 1858 are totally correct till today, up to today. There's still no real consensus on what is a blood-compatible surface, but blood interactions are clearly driven by surface properties, so we're looking in the right place. The fibrinogen albumin hypothesis still seems quite reasonable to us, and we're exploring this further. In arterial blood, highly hydrophobic surfaces seem to work well, and that's an important point, that we don't know that they'll work that well in low shear rate environments, but in high shear rate environments, we think they will. And non-fouling surfaces do seem promising. So that's kind of the conclusion. I think that's the last slide. But you know, looking at this path from 1972, we went, I think, from bad to worse in our politicians. But in any event, it's been quite a ride. And I think we're starting to get some insights in blood compatibility, which we desperately need for our dialysis system. So thank you very much for your attention.